Hello all. I'm Alan Whitkoff and I work at Maplesoft, and I'm pleased to show you some of Maple's numerical DE capabilities today. Um, we're going to start off slow, a little. I'm just going to give a quick introduction to dsolve. Dsolve is the primary command for solving ODEs in Maple, and the first solution I show here is an exact solution. For numeric solutions, quite simply, all you need to do is add the numeric option to the call, and it'll give you a solution procedure that can be used to compute values of, in this case, an initial value problem solution. And so I'm just going to do a quick comparison between the value returned here from the numerical solution computation and a float evaluated version of the exact solution. And to be fair, they agree with intolerance, right? So as I was mentioning, the return from dsolve with the numeric option is a computation engine. And as such, it can have modifications made to it, and you can continue to use it for additional calculations. So in this case, let's say instead of the initial value I originally chose as 1, I want to change it to 5. So I just tell the solution procedure, let's start at 5, and then I can query values using that changed initial condition. We can also, being an interactive procedure, query other things like how many evaluations were performed in order to obtain this result. And in this case, it took 50. We can then request a solution value at a time value greater, in this case 2. And we can ask how many function evaluations it took to get there. The important thing to note is that we're not going to compute the second directly from scratch. We're going to use a point in the region of the first computed solution and continue integration to get the second for efficiency purposes. Now, if we request a point further back, closer towards the initial point, we do need to reset back to the initial condition and start over. So in this case here, I'm requesting a value at 0.1 after having requested a value at 2. So it's going to restart from the initial condition of y of 0 is 5 and give you the computation you see here. So I just wrote this little loop here, and this is just going to do 100 computations at 0.1, 0.2, 0.3 out to 10 and give you a value at 10 at the end. We didn't need to do this loop, but this is just to show that if you request it after a bunch of additional requests in between, you get the identical value as requesting it directly after a reset. This is important for reproducibility and consistency of the output of dsolve numeric. Next trick, same problem, but I'm going to request a different output form list procedure here. And this now gives us a list of individual procedures for computing specific values. So now I'm just going to say, oh, let's look at this procedure here, which is the procedure for computing y. And now I can take this as an input into fsolve to find when is the y value equal to 100. And it just works directly. Okay. Next function to introduce is ODE plot, part of the plots package. And it's the primary tool we use for visualization of ODE solutions. And now we're just going to quite simply plot the y value from 0 to 4.6, which is what we figured out the value to be, where the y value goes to 100, and we get this plot here. And we can see, yeah, it's in pretty good agreement out to 100 there. It's important to note that dsolve, these examples are all very, very small. Dsolve can handle large systems of ODE, very large. It's used as the primary computation engine for MapleSim, and models can generate thousands of differential and algebraic equations to handle in MapleSim, and the solvers in dsolve have no problem with these at all. Okay. Going to show a little bit about problem points. So this ODE here clearly is going to have a problem at x equals 1 because of the denominator. So when we attempt to get the solution and compute it past that point, it tells us that we have a problem at around 1. And not only that, it's telling us it's probably a singularity. It has several heuristics, to be honest, to detect what type of problem it's running into when it can't integrate any further. Round off error, singularities, various other things, and it will try and report to the best of its ability what the problem is. It doesn't hurt to verify. So I'm going to do an ODE plot out to close to 1, and I can see that, yeah, we're getting a blow up. So in fact, it did report the right thing back. Less obvious, similar problem, y prime is equal to xy squared. This doesn't have an obvious singularity, but when we run it out to 2, it also tells us we have a singularity, in this case at 1.414. And again, we get a similar looking plot. Yeah, we're getting a blow up. Okay. One other useful tool for analyzing DE in Maple is the DE tools package, DE plot command. So the DE plot command can be used for first order inhomogeneous or second order homogeneous equations. And you can kind of think of it as drawing a field, which is why the DE plot command itself is 2D, because it has either 2 dependent variables or 1 dependent variable, and the independent variable can draw a field to give you an idea of where the solution is going to go. So if you're at a specific point here, the solution will go in the direction of the arrows. And we can see, and this being our first example, back here with the ODE and the singularity at 1, that when we look at the DE plot, the arrows at 1 look quite vertical. So a solution will flow in this direction and then blow up. You can also add curves to DE plot quite easily by just specifying initial conditions. So DE plot is actually a pretty full-featured code unto itself. There's all sorts of aspects of DSolve or DE plot you can use to visualize ODE solutions. So I'm going to give this system here, which is a 2-variable homogeneous problem. And then I'm going to ask for what the flow line, or I should say what the field directions look like. So solutions will follow in a circular rotation here. So you can then ask the question, well, is this likely to be something that's going to be closed, or is it a source or a sink? And if you plot a curve, and I chose some initial value, you can see it appears to be forming a cycle. So this is an excellent tool to get some insight into how your specific ODE system is behaving. It's got a lot of neat options too for producing nice visualizations. This one here, I've added the dir field option, and the dir field option just says, okay, give me a direction field, but give me 300 arrows or whatever you've chosen to use as an arrow, and position them randomly. So that's why we get a plot that looks like this. It's chosen random positions for the arrows, and we get something that looks less mechanical, if you will. This can be animated, and not just the curve, but you can also animate the arrows themselves. So I've created an animation here, 40 frames, and I've just said animate is true, nothing specific, which means that it's going to animate both the curve and the arrows. You can get specific and say just animate one or the other. So if you play the animation, you see that the arrows are moving as the curve is being drawn. Okay, there is an interactive tool that one can use, and it has a bunch of pre-programmed systems. that you can use, a handful of them that you can use to explore DE plot and also direction fields, and it's available via the DE plot interactive command you see here. One can explore a direction field, build a diagram that has a specific direction field, and ask for the command to be returned. And this is an example of what you would get for a returned command. So this is a sync in this case. In fact, it's the damped harmonic oscillator, this example. And so you can see the arrows are all pointing roughly circular, but you can see that the flow lines are heading towards the center point here. Okay, going to get into more on DSolve now. Maple handles quite a few classes of IVP problems. Stiff, which is pretty standard. Delays, it can handle delay equations. More will be shown on that in the workshop. DAEs, so algebraic equations combined with the differential equations. It's good at handling singular coefficients. And the last two, DAEs and singular coefficients, most notably require some degree of symbolic analysis to handle properly. So I'm going to give here the simple pendulum in Cartesian coordinates. It's probably the simplest index 3 DAE available. What we have is we have one differential equation on second order on x, one on y, and then a constraint on x and y, and also the unknown lambda, the fictional force. We just call DSolve numeric with this and no other hints, and it tells us, okay, we've got a solution for you. And you can see from the name of the variable, it's chosen a DAE solver for this. And we can quite easily look at a plot of x as a function of time. And DE plot, or ODE plot, I should say, can do expressions, all sorts of things as well. So what we're going to do here in this command, I'm checking to see what the defect is in the constraint. And this is actually the derivative of the constraint. And we can see that these actually have very good agreement down to 1e minus 8. So we have solved this DAE problem, and we are getting a consistent numerical solution for the constraint and its derivative. So to give an idea, and this is the simplest case, here. Yeah, so as I mentioned, larger systems can be handled. Singular points I mentioned also. This is Bessel's ODE, for the one for the Bessel, for evaluating Bessel functions. Okay, I've left the index arbitrary, but we're just going to pick one here. And we can look at the value of Bessel J1 at 0 and what the value would be at a half, keeping in mind that we need to use limit here because we end up with a 1 over x in the derivative. And we can just call DSolve on this. And it says the ODE system has a removable singularity. Initial data is restricted to y of x is 0. So what it did is we gave it a set of initial conditions, and it says, I cannot give you a solution that satisfies these initial conditions. There's a singularity. You need y of x equals 0 at the initial point. Okay, so we do that, and we get a solution. And I'm just going to compare the solution we get with the Bessel function. We see we get excellent agreement. The solution itself is in blue, and the plot of the Bessel function itself, or the Bessel function values, is the red dots. Okay. DSolve also handles boundary value problems. Simple boundary value problem here, y double prime minus y is 0. Y at 0 is 1, Y at 1 is 1. And we just look at the plot directly. And again, we can tell it used the boundary value problem solver from the name of the argument. And there are a lot of methods for handling more challenging DEs, specifically boundary value problems as well. The most notable for boundary value problems is something called continuation. And we have a full implementation of that in Maple. And we're going to cover that in detail in tomorrow's workshop with worked examples. Okay. All right, for this one, so there's an interactive mode that one can launch with DSolve Interactive. It allows for access to the full set of all methods available for DSolve initial value problems. It allows for boundary value problems. And it will compute exact and approximate. And I'm going to just quickly switch over so that I can actually show this to a full screen view. Give me one moment. Okay. I should be looking at my desktop now. Okay. All right, so, and here it is. So this is called the ODE Analyzer Assistant. Can everyone see the sub window?
Yes,
Yes,
it's
we
all
can.
good.
Excellent. So we can quite easily add in a differential equation. We can add initial conditions. Okay. Say done. And very briefly, I'll just show you can obtain a numerical solution by opening solve symbolically. And we can see in this case, I've chosen the differential equation and initial conditions that give us sign. And go back and go to solve numerically. As I was mentioning, the full set of methods available are here. Tolerance control is here. We can ask for function values at a specific value. We can obtain a plot. We can change the plot around. I'm going to go to a 3D plot. Find that. And I'm going to choose Y and Y prime and make the vertical axis T. And now we can plot that. Oops, one moment. And we get a helix. So as T in the vertical direction, the value is moving around in circles as a function of time. Nice feature about this, we can actually ask for the Maple commands needed to reproduce this. Okay. And when we quit, it gives us the set of commands. So everything we needed to do in order to solve this problem and to produce the plot that we were looking at is here. Okay. DSolve Interactive doesn't just need to be called empty. You can actually set a system in advance and it will just fill it in, of course. You can modify that. I'm going to edit this equation and I'm going to throw a parameter in there. Okay, and now you see you have access to the parameter in the parameters window. I'm going to choose something that has at least a little bit of a boundary layer. And we can go to solve numerically and just look at a plot of this. And we see that, yeah, we do have something with two rather relaxed boundary layers, one at either end. And on quit, we could return a plot instead. And this gives us the plot we were looking at. Also, context panel. If one enters this differential equation, okay, one can just immediately click into it via the context panel. Okay. I think that's probably everything I want to cover for the moment. I have several minutes left for questions. Actually, maybe I'll just briefly show this. This was a stiff initial value problem DAE, 2 index 3 constraints. It's a bit elaborate. There are 4 second order equations, 2 constraints. And it's the car axis problem. And we just solve it. In this case, we used stiff equals true as an argument because we wanted to use a stiff solver, and it used the Rosenbrock DAE solver. We can obtain the solution, and we can look at the plots of x on the left and x on the right. This is a kind of a 2-wheel car axis. And then we can look at the y values, and we can see that the right side, which is in blue, is much more active than the left for this model.